In these last couple of videos, we're going to be looking at using something known as Hess's law for us to be able to find a delta H for some sort of process that we don't know. And what Hess's law allows us to do is we can use, I'm just going to put this in quotes, pretend steps to find a real delta H. And we're going to use these pretend steps in a few different ways over the next couple of videos. One of these methods that we can do is we're going to pretend that you are breaking apart all reactants and forming products from pure elements. And so essentially we're going to be using a lot of delta H of formation. Now, that seems very confusing. So it's going to get a lot clearer. I'm going to jump right into an example and show you like what I mean by this pretend stuff. So here is a balanced equation. We're going to react nitrogen dioxide with water to form nitric acid and nitrogen monoxide. And our goal is to find the delta H of this reaction. Now, what Hess's law allows us to do is say, okay, we're going to break up NO2 into its elements. We're going to break up water into its elements, and we're going to take all of those and react them to make our products. And by pretending, we get to use the delta H of formation for NO2, for water, for HNO3, and for NO. We get to look up on a table all of those values. And this gets us really close to the actual delta H value for this reaction. And so here's how we're going to use these tables. All right, so let's look up the delta H of formation for NO2. So I'm going to go to a table here, and don't worry about like this G and this S. We'll get to that next semester. But this table here lists the delta H of formation for all of these compounds that we need. So the delta H of formation for NO2 is 33.2. So by pretending we're going to break apart NO2 and nitrogen and oxygen to make NO2, we get to use that enthalpy. Now here's the catch. All right, there's two important things you need to note. Number one, the stoichiometric coefficient from the balanced equation. I'm going to multiply this by 3. Here's the other important thing. If I'm looking at a reactant, I need to change the sign of the delta H because this is the delta H of formation. And what am I doing to this reactant? I'm destroying it. I'm deforming it. I'm going the other way. I'm not forming NO2. I'm taking it apart. And so I need to change the sign and make that term negative. Now, I'm just going to add this to the same thing for water. Now, this goes back to what I mentioned earlier in a previous video. I got to be careful because I'm using liquid water here, and that has a slightly different enthalpy than gaseous water. So I'm going to choose the right one here. Okay, so negative 285.83. I'm going to multiply this by the stoichiometric coefficient from the balanced equation, and then I'm going to, because it's getting destroyed, make that a negative. All right, now I'm going to add this to the products. So I'll look up HNO3. There it is. Actually, nope. See, I did the wrong one. I picked liquid. It should be aqueous. So that's negative 207.4 times the stoichiometric coefficient. I am not going to change the sign because I am forming HNO3. And then I'm going to look up NO. There it is, 90.25. Its stoichiometric coefficient is 1. Again, I am not going to change its sign because it's a product. So I change the signs of the reactants, or I basically multiply it by a negative, if you want to look at it that way. I don't change the sign of the product. And all I got to do now is just add all of these up. So negative 138.3 kilojoules per mole. And there's my delta H for the reaction. Now, the second way I can use Hess's law is I can mix and match chemical equations with known enthalpies to find an unknown enthalpy. I'm going to use the exact same reaction as before. So let's copy this back down again. All right, and again, we're going to calculate the delta H for this reaction. Now, let's say I didn't have a nice convenient table to give me the delta H's of formation. But let's say I have a series of reactions. So let's separate this that contain all of the components of my original reaction. So I know the enthalpy for this reaction. And then I know the enthalpy for this reaction. Oops. So delta H is negative 256. And then finally this reaction. Okay, so think of this like a puzzle. And what I'm going to do is manipulate these three equations to eventually add up to this one. Okay, so I'm going to take these equations, I'm going to flip them around, I'm going to multiply, I'm going to divide by stuff, and eventually I'm going to get to that original equation. Okay, so let's start with, let's see here, NO2. Because I see, well, let me use a different color than that. There, because there's an NO2 there, and then there's an NO2 over here. Okay, so notice that over here, the NO2 is on the product side. I need my NO2 to be on the reactant side. So I'm going to rewrite this equation to put it on the reactant side. I'm going to flip it around. Now, here's the important thing. The delta H of the first equation before I flipped it was negative 116 kilojoules. Okay, so if you flip an equation around, you're going to change the sign of the delta H. Now, the next thing I'm going to do is address the coefficient. Okay, notice the coefficient here is 2, but in the original equation, it's 3. Okay, so what I'm going to do now is take all of these coefficients and multiply them by 1.5. So now I have 3 NO2, 3 NO, and 1.5 O2. I know that looks kind of weird. That's okay. Again, remember, these are pretend things. So we can kind of, I don't want to say break our rules, but we can kind of temporarily suspend them to get to the final thing. And the final thing will make sense once we manipulate the rest of them. Now, what do you think I should do? If I multiply the moles or those coefficients by 1.5, what should happen to my delta H there? I'm going to multiply it by 1.5. So that comes out to 174 kilojoules. Now I'm just going to kind of, I'm going to put a little circle around that because I don't want to lose track. I'm going to come back to that eventually. Now let's take a look at water. Okay, so I'm going to go back to my original equation here. There's water as a reactant. I'm going to look through my equations here and I see, oh wait, there's water right there as a reactant. Okay, now it's as a reactant, so I don't need to flip the equation. But what do you think I should do to revise it? Because my balanced equation here has a coefficient of 1, and this is a coefficient of 2. I'm going to divide everything by 2. So divide by 2. And so now I have N2 plus 2.5 oxygens plus now I have 1 water and 2 HNO3. Now, if I do that, what do you think should happen to my delta H here? Because I have half as many moles now. I'm going to divide it by 2. And I'm going to circle that to keep track of it. All right. And now what I'm going to try to do here is sum up these first two equations. Because notice that I have my reactants taken care of. All right. I have NO2 here as a reactant. I got water here as a reactant. I got NO as a product and nitric acid as a product. Okay, notice those are my 4 things up in the balanced equation. And so let's add these 2 equations together. Okay, now when I add, I can start canceling out things that are the same. Okay, so I have 3NO2. And then I still have a nitrogen. Notice I have oxygen on the left and oxygen on the right. So I can cancel a little bit of it. I can get rid of this one completely and have 1.5 oxygens there, plus water, and then 3 NOs and 2 HNO3. Now, does that look anything like my original equation? So the original equation's up top. Well, there I have 3 NO2s. That's great. I got one water, that's great. I got two nitric acids, that's good. But that doesn't look good. Nope. There's no oxygen in my original balanced equation. And I should only have one NO in this. Okay, so how do I get rid of, because I got to get rid of the nitrogens, I got to get rid of the oxygens. And I realized I added this up incorrectly. There is one oxygen there. Sorry for that. 2.5 minus 1.5 is 1. I'm sorry about that. Okay, so I'm going to go back to my original given equations here. And notice I have a third one I haven't done anything with that has everything in it that I want to try to get rid of. I need to get rid of two NOs, and I need to get rid of a nitrogen and an oxygen. Well, that's what that third equation is there for. So I'm going to take this third equation and I'm going to flip it around because I want to get rid of some NOs and I want to get rid of the nitrogen and the oxygen. Now, if I flip that around, my new delta H is going to be negative. Notice what happens now if I sum these two equations together. Okay, the nitrogens cancel out, the oxygens cancel out. This NO goes away, and I subtract this one by 2. So what I have left looks like this, and that is exactly what my original equation started out as. Okay, so I got to my original equation, big deal. Well, now I'm going to take my enthalpies from each step that I manipulated, and I'm just going to add them all up. All three of those add up to negative 137 kilojoules per mole. And I want you to compare this to this same exact reaction that we did on the previous page. Notice that it is actually very, very close. And in reality, these are kind of close estimates. We won't know what the delta H is until we get into the lab and actually do experiments. Then we can find the exact delta H. These, using Hess's law to kind of do these approximations, are just that. They're going to get us close to the real answer, but not right on the real answer. So in the final video, there'll be one more in this. We're going to look at one more use of Hess's law and looking specifically at the energy involved in breaking bonds and forming bonds.